Rational numbers, an official name for fractions. Fractions made up of two different parts. We have top number, referred to as the numerator. We have the bottom number, referred to as the denominator. The whole purpose of fractions is so that we can take something and break it up into parts. All those parts have to be exactly the same size though, which is a limitation that we've got with fractions. We can, however, pick however many parts we want to divide something into. So just as an introductory example, if we're looking at a chocolate bar, and we can have that chocolate bar broken into 8 equal parts, let's say that I wanted to have a little snack, and I was going to have only 3 of those pieces, then I can use the fraction 3/8 in order to represent that snack portion that I would be eating. We want to be able to compare fractions, which means that we've got several different sort of possibilities we could talk about, or we could just go with the most direct route for comparing things. Just to cover the bases, certain special cases, we can do maybe a quicker comparison. If all of our fractions have the same denominator, then we can compare numbers the same that we would as if we had no fractions at all. 3 is smaller than 4, which is smaller than 5. But we can also actually end up having a pretty quick comparison for a very different situation, where instead all of our numerators are the same number, while the denominators are different. And what you see here is a circle with a pi wedge to represent these 3 different fractions. 1 out of 5 in blue, 1 out of 4 in green, and 1 out of 3 in red. By drawing those pictures out, we can actually see that the blue slice is the smallest, the green slice is in the middle, red slice is the largest. So this, other than the chocolate bar, now gives us another way of representing fractions in a realistic sort of way to try to get a grasp of things. Cake, pie, pizza. We can use that sort of basic idea to help ourselves as well, if we need to. But these are very particular rules, and we don't absolutely need to know them in order to compare fractions. And in fact, we might not have any better way of comparing fractions with rules or pictures, and we don't want to be stuck. So what we do is we have a way of trying to create a comparable situation. I'd like 2 regular numbers that I can compare very quickly, and the comparison between those 2 friendlier numbers would end up leading me to figure out how I would fill in this box. Should I say that 3/4 is smaller, the same as, or bigger than the fraction 11/15? What we want to do is called cross multiplying. Now it's very particular that we have to start with the top number. So when we are looking at this particular situation, we start with the top number of the first fraction specifically, and then we create part of a cross shape by then using the bottom number of the second fraction, so that's the cross, and the multiply means that we take those 2 numbers and multiply them together. In order to create the other bar on our cross shape, we would use the other pair of numbers, the bottom of our first fraction and the top of our second fraction. So now we would have a means of comparing more normal, more familiar numbers. 3 times 15 is 45. And 4 times 11 is 44. The symbol that I would put in between those 2 is the greater than symbol. And as it turns out, I would want to take that greater than symbol and carry it all the way back to that empty box. So the fraction 3 over 4 is greater than the fraction 11 over 15. This method of comparing fractions, this cross multiplying, is something that would work no matter what two fractions we have, which means that we don't need to remember any sort of special rules if we don't want to, in order to do a comparison between any two fractions. Like this example, I can do the cross multiplying. While we don't use this very much here in Chapter 3, we will see this working to our advantage when we get to Chapter 5 and start discussing ratios. For right now, cross multiplying would only be used to compare two fractions and decide which one's bigger, which one's smaller, or if they are in fact the same. To continue with the kind of introduction to fractions, I want to mention another way that we could try to visualize things by using this example. I want to take this fraction 10 over 12 and I want to estimate that. Is that number 10 over 12, that fraction 10 over 12, closer to 0, closer to 1/2, or closer to 1 whole? Well, if we think about what we would normally have split up into 12 parts, 12 inches to a foot, which means that a ruler idea could also sometimes be helpful to us. So we'll go ahead and start making marks for that ruler idea. We'll make those marks a little bit closer together so that they all fit without going. So each one of these marks represents 1. And if we go all the way down to the end, 1 mark for 1 out of 12, 2 out of 12, 3 out of 12, all the way down, this is 1 whole, or 12 out of 12. We want to know where the halfway mark is, and the halfway mark would be right in the middle, where we have six over 12. So now we know where those markings are. That's great. Where is the 10 over 12 going to end up being located so that I can make a comparison and see, is it closer to 0, 1/2, or 1 whole? Well, 10 on top, meaning I want to count out 10 parts out of these 12. So 7, 8, 9, 10. So I want to mark the fraction 10 over 12 at this particular location. Now, just purely based on a visual comparison, that green mark for the fraction 10 over 12 is definitely far away from the 0 mark, which means I've narrowed it down. Is it closer to the 1/2 mark or the 1 whole mark? Well, visual comparison, I'm a little bit further away from 1/2. I'm a little bit closer closer to 1 whole. So the fraction here would be rounded or estimated to 1 whole. Little squiggly equal sign for that approximately equal to or about equal to. So again, really the main idea here is to show you just one more way that you can try to visualize fractions, get a handle on what's going on, really understand what we're getting at with them before we actually start doing any work. In order to actually start doing any work though, we need to take a little side detour because we're going to need to know a little bit more about working with numbers to eventually be able to properly work with fractions. So some side comments about numbers. What we're talking about here is breaking numbers apart. Kind of goes along with the idea of fractions. Fractions break things apart. So we can break a number apart into a multiplication problem, and we're referring to the word factor as the piece of a multiplication problem is a factor. For instance, if I wanted to take the number 24 and break it up into a multiplication problem, the most basic way I could do that is 1 times 24. So I could say a factor of 1, factor of 24. I could also say that I could break that number 24 apart as 2 times 12 or 3 times 8 or 4 times 6. But there happens to be one more possibility where I would have things broken apart in a multiplication problem, and all of those individual little pieces would be the smallest possible numbers that I could come up with while still using whole numbers. And that would look like two times 2 times 2 times 3. That would be taking the number 24 and breaking it apart so each factor is as small as it could possibly be while still being a whole number. Well, it turns out that might be a helpful sort of idea to utilize. What we're talking about here would be numbers that are called prime numbers. Those smallest building blocks, they cannot be broken apart into any other factors. Composite numbers like the number 24, these are numbers that can be broken apart as 2 or more different factors. Well, what if you don't remember all those prime numbers? Well, we've got an ancient way of being able to sort out which numbers are prime, referred to as the sieve of Eratosthenes. What we've got going on here is an arrangement of numbers, and we can use the idea of sifting out in order to find the prime numbers versus the composite numbers. One quick comment here at the beginning. Officially speaking, 1 is unique. It has its own name. It is the multiplicative identity. Because that is so darn special, we do not actually refer to it as prime or composite. It's just so darn special it gets its own name and stands out from those other 2 possibilities. Which means we've already started the sifting process. 1 off the books. That means the smallest number that we now have showing up is the number 2. 2 is the smallest and first prime number. So let's circle that. And now let's work through our arrangement of numbers and cross out any numbers that have a factor of 2. Or another way we could say it is, let's cross out any number that can be divided by, divisible by, 2. Which means all of our even numbers are going to be crossed out from our list. Now we would want to go through all of these numbers. When we get to the end, we go back to the top of our list and we select the next smallest number that has not been circled or crossed out. So, after all of this, we're going to return to the beginning of our list of numbers, and we see that we have the number 3. It has not been circled or crossed out, so we will circle it as it is the next smallest prime number. Now we go and sift through our list again, looking for any other numbers that could be divisible by 3 that haven't been crossed out. If they've already been crossed out, they're off the list. So the 6, already been crossed out, I don't need to worry about that one, but the 9 is divisible by 3, hasn't been crossed out yet, and I need to start slashing. So once again, we're going to make a pass through our list and we're going to slash out any of the numbers that are divisible by 3. Until we get to the end of our list and we are able to return to the top once more in order to select the next number that has not been circled or crossed out, which is the 5. That means the 5 is the next prime number. We would continue to make passes through our list, circling and then crossing out any numbers that needed to be crossed out until we have no numbers in our list without a circle or a slash. If you take a look at the notes, you'll have a finalized version of this where all of the prime numbers will be highlighted. After the 5, we have 7, 11, 13, and you can check out the list in the notes for those remaining circled prime numbers. If you think about it for a moment, it might seem like it's very understandable that if I took any number and broke it apart so that only prime numbers showed up, that string of prime numbers would end up being a unique string, so that I would have this unique multiplication problem. Sounds pretty good, not very obvious, but this is what we want to actually do when they tell us to find the prime factorization. And this is a useful sort of thing for us, which we will bring back to the fractions here in just a moment. Let's go ahead and start and try to be organized. Let's use our smallest possible prime number first, if possible. Does 2 go into 756? Sure does. So we can break off at 2, and we would be left with 378. Now we want to go ahead and take that 378 and break it apart even more. Let's not ignore the fact that another 2 might be usable. Certainly is. 378 is an even number, which means that we can go ahead and break off another 2. So that means that we would have a blue 2 and a green 2 If I take the 378 and divide it by 2, then I'm going to get the number 189. Now, as far as the number 189, that is not divisible by 2. So I've used up the prime number 2. I've peeled off as many of those as I could. And now I'd have to move on and consider other possibilities. Well, the next possibility is the prime number 3. Will 3 go into 189? Turns out that it will. So we're going to continue having the blue 2 and the green 2. Now we get to add to it a red 3. 3 will go into the number 189 63 times. Well, now we finally see a number that we might remember from our times table, which means we've got a little bit more flexibility with trying to break that apart the rest of the way. But let's continue with the pattern that we've been using. Since we've used the 3, let's go ahead and see if we can use it some more. Will 3 go into 63? Sure will. 3 will go into 63 and give us a 21. So we're recopying all of these numbers to blue 2, green 2, red 3, now a pink 3, and the 21. The 21 can now be broken apart. We can use the number 3 one last time so that we have in our final answer blue 2, our green 2, our red 3, our pink 3. We break off one more 3, we'll put that in orange, and then we have a 7. So now we have only prime numbers that are appearing in our big long multiplication problem. So this might very well be an acceptable answer. We would have to watch out for the directions. If we had any specific directions about giving our answer, they could ask us to use exponents, which means that we could shorten this answer up by taking the 2's, combining them together so that a power would be used, taking the 3's and combining them together so that a power would be used. That answer would have 2 to the power of 2 and 3 to the power of 3, and times by 7. We do not need to put a power on the 7. There is only one of them. We do not need to emphasize that by having the extra power of 1 on that 7. Let's see if we can use that idea in a useful way with our fractions. We would be hoping that it would help us give the simplest possible fraction as a final answer. We can say simplifying as a generic way of talking about what we're doing. We could say reducing to be a little bit more specific. And the basic way to perform the reducing would be to completely factor both the numerator and denominator, both the top and bottom of our fraction. Then look for any factors that show up in both the top and bottom. By removing those, we're not changing the actual fraction, we're just changing the way that it looks to make it look nicer, to make it look more friendly, so that we would have smaller numbers on the top and bottom. You can think of money as a helpful way why we would do this. If I wanted to hand somebody 50 cents and I wanted to do it in the fastest possible way, I would not want to hand them a handful of 50 pennies. I would not even want to hand them 5 dimes. I definitely wouldn't want to hand them 10 nickels. I could hand them 2 quarters, and while that might be fairly realistic, the absolute possible fastest way to give somebody 50 cents would be to give them a single coin worth 50 cents. And so the simplest version of handing a person 50 cents would be to give them that one coin, the 50-cent piece. Well, the money version is working with this sort of idea. I want to peel off all that excess so that my final answer is the shortest, sweetest, prettiest. It has the smallest top and bottom numbers that are possible. It's a bit overkill to have to go through and do this, though. When you start thinking about it, I have a 6 on top, I have an 18 on the bottom. 6 would go into both of those numbers. Could I just get there faster by saying that 6 goes into 6 one time, and 6 goes into 18 3 times? You certainly could, which is what realistically we would rather do when we're simplifying fractions, yet we're still using the idea of factoring without quite beating ourselves up about those prime factorizations. So, as a last example for the video, let us simplify the number 42 over 48. To try to do this as quickly as possible, we want to think about what we know of multiplication and say, what is the biggest number that will go into both 42 and 48? And that number is 6. 6 goes into 42 7 times. 6 goes into 48 8 times. So we can go ahead and slash out the 6 on the top with the 6 on the bottom to leave us with the fraction 7 over 8. Just to play it safe, any other numbers that will go into both a 7 and an 8? No way. So that would be my final answer. The reduced version of 42 over 48 is 7 over 8. So we've used our factoring ideas without quite going so far as using a prime factorization. Gives us the gist without having quite so much time or effort involved in getting that final correct, simplified or reduced, or you could also say in lowest terms answer.